I want to introduce Clinton Smith and Stephen Davies from Leica Geosystems, which is part of Hexagon. Gentlemen, please introduce yourselves and give us some gee whiz in the tech and systems. Thank you.
Thanks, Kevin. Let me get myself set up here and I'll start sharing my screen. In the meantime, I'll give you a little bit about myself. I'm a product manager at Geosystems. Have 15 years experience of being a product manager, a diverse experience, if I might add, which gives me the option to really use my skills and my experience to help develop some of the solutions that we looked at, some of the solutions that Jeff was talking about in detection and in mapping. So I'm excited to be a part of it, and I'll let Steve mention some of his talents as well.
Maybe not all of them. Hi guys. Yeah, it's Steve Davies here from Leica. I've got 30 years in the surveying trade. I'm part of the product management team working with Clint to test, develop, introduce products to the market, and most of all, train on the detection products, calling on all my experience to help people around the world globally, to be honest. So I'll keep it short and sweet, and we'll get Clint kicking off.
So as we probably have already heard, why are we here? I think today is going to be an exciting day for those of us participating in this event. We've already off to a fantastic start, listening from Jeff and his comments and his experience. I hope you realize as we go throughout the day that it's going to build on each other. The things that you learn today, bits and pieces of it you can take with you. And I hope you have, at the end of the day, a lot of takeaways that you can use in your applications, in your development of maps underground. Part of the reason why we want to be here today is to show you what you can do with detection tools, combining them together with positioning sensors to give you those accurate maps that we talked about or heard about this morning, being one of the critical roles in mapping, underground mapping, and exploring or seeing or unveiling the unseen. Some of the things we want to focus on in this presentation here is how important is that, and I'll briefly touch on it because we've already heard some of it, but it's utter importance that we have this correct, that we do this right, we don't skip this step as far as it comes to underground mapping and seeing what we don't see. And Steve will then talk about a little bit more on the accuracy of it, what we need to do, some of the tools and combination of things that we use to do underground mapping. And you've already heard from EM or ground penetrating radar. Those things are part of the package, and it's putting this together that makes it work together. And this is what we want to cover in some of this presentation here to show you. Also some basic case studies where this applications and what people did to solve issues or overcome a problem that they were seeing. And it wasn't until they put this ground penetrating radar or EM together and discovered what they needed to do. And then finally, I only want to touch on future, where it's going with what we expect to see coming out of it. So when we look at smart city, because what is a smart city? And yeah, contrary to what it may sound like, it's not a bunch of people with high IQs living in the same location. That would be there, but it's not what it is. It's deeper than that. So it's using the technology of what we have and sharing that technology. And we've heard already briefly that we may have the technology, we may be able to piece this technology together, this information of what is lying below the ground. But it's not until we start sharing that information with the general public or with a developing city that we then start making the city smart. And we start being able to use that data in a good way. So we might use a tool like a EM tool where we're going around and tracing a line in the ground and putting together this information, but putting it into a useful information where it can be used later. And this is part about developing the city. It's also part about making a safe construction site when we can use these tools to identify what's in the ground, what's below the ground. Before we break the ground open, we know where and where we shouldn't be with the digging tool, with the extractor, so we don't have any issues here, because they can be and they will hurt us. It's also when we have an open trench, for example, before we bury the pipe, there are tools that we can use with our portfolio, with Hexagon. We can do above and below ground mapping. You combine this together and you know what's there before you close it up, so that you can build this map as you go and use it in the future. Or if we're in an urban area and we want to see what's there, a number of tools can be used to combine this information together and develop something that we can use later on. And the other thing, it's developing so fast, and we'll show this to you a little bit later, but we also have the technology that can gather this information at speed. So when we're talking 35 miles per hour up to 90 miles per hour, you're capturing data this fast and processing it, back processing, but it's now faster than ever to use again. So this adds to the smart city that we are talking about, and it's then using this information to go forward to help develop that city. But it's also another aspect is the critical part. We've heard this: safety, safety, safety. If you don't use this, if you stop doing the rules, or if you try to cut corners and you avoid this, it's more costly than what you think you will save. You might cost a life, you might cost injury, personal injury to somebody else. And the other items in the list are obvious: unforeseen repair cost or downtime or such, and this is also costly money-wise. But I think we should really be concerned about the number one thing on this list, and that's personal safety, to avoid that. And this is something that we can do. We see regions that are implementing the right tools and the right legislation to avoid this. And this is our number one focus that we want to make sure that we do. So when we start talking about the tools that we have and how we can combine them together to make something safer, we can do that by combining a couple things here. So we now have a electromagnetic locator going through, looking for things into the ground, and we like to use this kind of a workflow to combine the technology so that we don't leave anything missed. So no stone unturned. We can go through mark some areas. We use a GPR to go through, cover that area, and it's picking up bits and pieces, and you link them together with a sensing position device or a sensor, GPS, if you will. You can start getting a complete picture of what's below the ground. And then you can start using that right away on site by analyzing this information, sending it over to the operator of that machine to help avoid any kind of injury at the site. And this is where the accuracy comes in. This is why we need to have the tools to be accurate, to be spot on, centimeters, 5 centimeters, right on, so we know what's there and what we can avoid. And I'll turn this quickly over to Steve, because he's going to take over and give you a little more about accurate underground mapping and some of the tools and techniques that we use in this area. Steve, if you would like to try to take over, and I'll give you position of the controls.
Thanks to Clint. Nice intro. We had a very nice intro from Jeff. Thanks very much. And that kind of laid the foundation stones for us going forward. If I can just get into my presentation and it'll work. So the detection portfolio that we have here at Leica, and Hexagon, sorry. Oh, my presentation's just there, 2 seconds. There we go. Just get rid of this. Okay, get my face off the screen. This is a detection pipe, and we use it in many of our presentations because it shows a complete picture of the available solutions that we have. From large-scale aerial photography to detecting buried infrastructure, from working within live construction sites, finding existing pipes, cables in the ground, and to the things in between, which we call surveying. So whether these are below ground, above ground, or on the ground, Hexagon claim all three because these are things that are in our portfolio and part of our solutions. So smart cities have as much, if not more, going on below ground than what we don't see. As to that you do, the eye candy of the nice building. Clinton's mentioned previously to detect a map, we need to look out for these. Lead on from Jeff, EML, it's electromagnetic locating, and it's process of locating using cable locating. You should all be familiar with these tools. But the reality is, these machines find electromagnetic fields, predominantly found around pipes and cables. So we need to learn how to use the kit. Hello, I'm a trainer, this is what I do. And, you know, we'll move on to the second one, GPR, short for ground penetrating radar. It's a similar electromagnetic device and transmits and receives signals to from a medium being investigated. The results are then interpreted by the system, and an image of the subsurface is given on the ground. We make it sound ever so simple. There's a certain amount of knowledge and skill involved to use these. GPR is a much more wide-ranging term. These are two terms that everybody uses, guys. And so we use the GPR to describe one, a piece of equipment, and two, the actual technique for what we're doing. Did we GPR the ground? This technology, GPR, is capable of detecting both metal and non-metallic objects, whereas EML is for metallic pipes and cables. It's up to us to gather the skill and knowledge to use it, unfortunately, as Jeff touched on. So with those two out of the way, for anyone involved in the detection of buried assets, EML and GPR are the go-to tools. Little description on the screen there of what we've got. They've both been around for a long time. EML for around about 100 years, a little bit more, but the operating principles and theory of how and why they work, they really haven't changed. That's why we see old and new equipment models being used on work side by side. They come in various shapes and sizes. On screen at the minute is the original GSSI radar, van-based, and some traditional radar data. Both are capable of doing the data thing, of collecting real-time centimetre accurate positioning, not something just loosely mapped in satellite imagery with an accuracy that is really not good enough when we have to break ground. Most people know about and are aware of cable locators nowadays, and their importance within the construction world. Not only for being able to find things, which is their primary function, but equally and more than the primary function is safety, to keep people safe. GPR follows suit, and it should be used that way, preferably in conjunction with an EML device. For me, the site workflow starts with a locator. Naturally, existing pipe and cable record plans would come first, but they aren't always available, and neither is an 818, 811 locator. As we know, there are many manufacturers of locators, all shapes, all sizes, and all colours, but they all do the same thing. For more complicated locates and in-depth surveys, we use a precision locator system, and with a little help from a GIS data collector, like on screen now, GPS centimetre accurate data can be possible. On the screen, I was collecting to less than 5 centimetres accuracy when I was doing this. We currently use a modular system, as we know that one size doesn't fit all in the locating world. So the type of system lets other manufacturers from other users who want the ease and simplicity of RTK detection, they can come to the party too. This is a bolt-on system, guys. So a simple pairing of devices, a small setup, and away we go. The system you see here is in the process of a simpler, smarter, more efficient revision, with a totally new solution coming very soon. So I advise you to keep your eyes open for it. It'll be good. Output from the mapping app is into the GIS platform, ArcGIS, where simple data conversion allows exports to the CAD modeling world with 3D attributes. So we mustn't forget that locator ranges, with all the usual accessories, are as important as the key components themselves, the transmitter and the receiver. So we can add these accessories to the variety of tasks to make 3D data capture more accessible to everyone. If we use EML, it's the ideal partner to any GPR task. It's a Batman and Robin, if you like, of the detection tag team. And it should be used that way, as a partnership. I've been lucky enough to be involved in the DSX project, if this video will run okay. I've even had my own Hollywood moment in this video. This handcart system, with its all new software, intuitive. It's now available. This means that previous non-GPR or less experienced users can now get into the equipment, use it with relative ease and accessibility than ever before. Peeling back the layers and trying to democratize, if we want to use that word, the accessibility and availability of GPR. Take it away from, not take it away, but make it less non-expert. I've used this system, I've used GPR for 20 years, guys. It's quite simple to use, does things very nicely. As you can see on screen, we can get live 3D cube data. The machine and the software does it all for us. The only thing we have to do is simply select the target, which is shown in the high amplitude on screen. We can set coordinates to export. We can use it on any type of surface. As long as the wheels go around, that's us collecting data. What a handsome chap. And we have onboard, from site reporting. Simple, planimetric, or data analysis. We can peel back the layers for any kind of type of construction. So, ground penetration radar, or GPR, or if you want to call it the dark art, it's always been a tricky process to pitch to the construction world. Thought of as overcomplicated and difficult to understand. Well, things are changing. They've changed already. Traditional view of GPR data is replaced with a top-down view and slices through the ground. The unique operating software allows you to position EML detections within the data that you collect your site. You can easily assign the correct depth elevation for the EML device, and for the first time on site, combined EML and GPR data come together in the same 3D live cube. This ability with the intuitive and powerful detection algorithm for target analysis gives the DSX the edge for simple efficiency. Add to this a GPS sensor for positioning, then all the data, including the EML information, inherits a true centimeter XYZ position. When used with the correction service, all available live on the worksite for the first time. The first time we'll see it in collection software, to be honest. Other systems in the portfolio, Handcart Rage has a more traditional approach to how it does things, as you can see on screen. But the same applies, and you can still record everything on site, including EML and assign true centimeter XYZ precision into targets, TPS, total station, or GPS. GPS surveying. You just have to know how to get the best out of it. Sorry guys, but I'm a trainer, and that's what I have to say. The multi-array antenna systems are perfect for larger area coverage, while the handcarts tackle the smaller and maybe less accessible areas. The latest array, Clint's always already mentioned this, is the new kid on the block, because it is. If you want to then bring the latest signal processing techniques for our high-speed highway data collection. All systems have positioning available to them, and all have 3D export and post-processing capabilities. The combined efforts of EML and GPR together get the best results possible. We use them together. And software, well, that's the glue that binds all this together. As the industry moves forward with this, taking ever larger steps day by day. So take DXplore as the latest example for acquisition software. Trying to keep us away from the hard and difficult interpretation. So with the innovative process of Hexagon, we're ensuring cross-divisional collaborations, cementing the path to the future. The goal is to create a one-stop solution where the equipment, its firmware, and the software all seamlessly integrate with each other. Quicker, smarter, and with greater accuracy and efficiency than ever before. Let's call it total mapping, if you like. And with that, it's back to you, Clint.
So we have a lot of information so far coming up. What I'd like to show you now is just a few of the case studies that we have. This is using multiple different types of tools that we use for mapping or detecting what's underground. Some of these cases are from the US, some of them are from other parts of the world, but I think they paint a pretty good picture of how we can use these tools and how we can use the equipment to give us the unseen world and bring it to our fingertips so that we can have a better picture of what we have below. This was using a array system here. What we're going through is looking at a road here, trying to map out underneath it. I'd like to thank the team over at T2 Utility Engineers for providing us with this case study. They did this in a couple of different steps here to use this equipment to map out what they had underneath. And the nice thing about this example here is they combined a bunch of information to eventually get what they wanted to complete their SU information, if you will, or to at least update it a few levels to make it more clear as to what we have. A lot of sites that you know don't have complete information. They may not have dated information or up-to-date information, and you need to start putting the puzzle together before you dig, before you start going into the ground and seeing what just needs to be added to it. So what they did is they used a couple passes here to help identify some of the sewer lines or the water lines in the ground to identify the locations of them. But then they used also EM to go through and identify some of the other utilities with here in blue and red and green, and overlaid them now on top of a single map so that they could see the whole picture. And I say now the whole picture is because in this image here, you see there are some areas where the radar was strong, there were some areas where the EM was strong, and it's not until you combine these two together that we have now a complete picture, a complete image of what's in the ground. And this is what is important here, is we start getting in now to a complete image, we start processing all this data and adding it together to give us a better view. And it's how we look at this data, or how we want to use this data to our advantage when we do future development or when we do future studies. And it depends on what equipment you have. It depends on the software you're using. When you start collecting this data, it starts to add up. It starts to accumulate. You have a lot of data. One of the examples I want to show you here now is one of the systems that we've just released out. It's not too long on the block here, and this is a stream up. It's something that I'm sure Gavin is very familiar with, but we're starting to use the software here to make a complete picture. So if we look at an image here, when we want to start this video, we can see then how this information is loaded, how this information is starting to be pulled together so that we can use it to our advantage. So if we think about loading up a project that you'd had to maybe do this back office, of course, and you're starting to process the information, you can do this much quicker now with the right software, with the tools that we're developing, to go ahead and start loading up an interesting area or area of interest to where you want to see or combine now what's above the ground to what's below the ground. And in this example here now, you can see what we're finding in an area we have interest. We're using now the radar data that we collected, and I will go again with the note that Jeff mentioned. We are doing some of this data collection at speed. So this unit here can go up to 35 miles per hour is where they recommend, but you can go up to 90 miles per hour and then create this information. You can create this 3D image to where you can now look at the data in a different way and more something that's easier for us to visualize over vast areas. And this is a lot of information. And this is being processed at much faster speeds than we had before. So this helps us to get the answers we need in shorter time to be more efficient and more complete with the data that we're using here. And these are the kind of tools that we like to use for this. And these are looking for utilities in this case here, but the tools are not just for utilities. It's for finding out what's not there or what's there that we don't see that's not a part of the utility, that's not even on a map. So when you start looking at some of the areas in this diagram here, you may see some areas that looks like maybe it's a trench, maybe it's a piece of pipe. Who knows, maybe it's a Model T Ford that's been there for about 50 or 60 years or 80 years. Don't want to dig it up. Maybe what's inside you don't want to know. But it's finding information that you don't know. And this is what's very critical for somebody that's working on a site. It turns out that this, what they suspected to be the old railroad tracks that were buried on the site. But when we start looking at the big picture, and this is where this information really comes in, and this is something that we've alluded to already in today's presentations, you've got to be responsible for what's on the site, not only for what's above the ground, but for what's on or below the ground. And when we start looking at this in this respect, then you know what you really want to know, what's below the ground before you invest in this piece of property, or before you invest in this ground, so that you can have an idea what you may be dealing with. You might want to find things out beforehand rather than later. And this makes a big difference. Here's another site that was in Europe. We had the information, but it was limited. We didn't have all the data here. We have on the diagram on the left some drawings of an area they wanted to do, trying to find out what's not there. Let me turn the screen here to the right screen.
How to do this again.
You have this here now where you can see parts of the information, but not all of the information. So we used, in this example here, we used a push cart GPR mounted system with a GPS locator. So we're using positioning and radar combined to complete the picture. So we're doing a pseudo array here kind of thing, a pseudo matrix, where we're doing the scan here to get the information that we needed to see what's in the ground before we went any further with this. So when we start building this transformer station, we have the information that we need. And again, this is combining tools, combining the things that we need to have to get the accurate mapping of what we want to see before we go any further. Just a light example here as well. We have also an example here where we're taking the data from a push cart with a GPS location and putting it into, and now getting a depth image, getting a 3D drawing here to use this data before we go further with it. And the only reason why it's in red here is because the operator preferred the contrast of this image before they processed it, and this was the only way they could best represent it. But as we move forward, as we start going into different ways, we can actually think of how we can see this data differently. It's all about visualization and how we want to maybe look at this data maybe by a flyby. So we can now go through and we can map everything out in detail. We can look at it from above, from below, from the side, and we can get a good idea of what's there and how accurate our maps. And actually, you can see when we go do this kind of flyby here, you might be able to see areas where the data is missing, where it's incomplete. And you can also find maybe the tools to help you complete this data even better than what you had from before. So it's like a big puzzle that you're piecing together, these technologies, these tools, this equipment, and getting a better picture for it and getting what you need to help you become more safe and smarter with your future. When I talk about future, what is the future? We've touched on this already before, but it's an amazing prospect that we can look at here, because now we're having technology, we're having the information coming in from all sorts of different channels, all sorts of different types of tools, all sorts of different types of equipment can be now integrated through a common glue software where it's picking the information and filling up the gaps that we might have at a site, at a construction area, what have you. We use this information, and we see the future is this happening more and more. And we've already alluded to that. We have information from GIS, ArcGIS, we have machine control information. All this stuff is being used to help us be more efficient, to be more safe, to be more productive. And when we start seeing this information being pulled together, and this is where I feel that we have a good advantage here at Hexagon, is we can bring this information together from all perspectives, both in the ground and under the ground and on the ground. And another thing about this future is we're starting to do smart learning. We're using platforms like Excel to take this information and go deeper with this information. And I think this is something that we're going to see more of, where we can see information coming in from artificial intelligence. You're learning as we go. It becomes a smarter GPR or a smarter EM locator, or your visualization is a little bit better. Maybe you're walking down to a job site and you're wearing glasses, virtual glasses, and you can actually see the pipes in the ground. You don't even need a handheld device anymore. You know that it's 3 meters or 6 meters or feet down below you, underneath your feet, what's there and what kind of utility it is. But the future is going to be an amazing spot here, and we're going to be able to play a fantastic role into developing tools that integrate with each other, and hopefully we can get past some of the sharing of information to other people so that we can learn and help save lives later with this information. And these are the kind of things that we want to be a part of. These are the kind of things we want to contribute to. And I see the future as doing something just like this as we go forward. And it's going to be a critical role in it. So what did we talk about? We have a fantastic session here. We have an exciting day. And our part of it is just a tip in the whole picture, but it's a fantastic part to be a part of. Underground mapping is just beginning to really take in, and it's really beginning to see, hey, this is something that we should be a really good part of, and we need to be active doing this. We need to be a part of that smart city. We need to be a part of that safe construction site, and we need to put that at the top of our list that it's there, and use that information, share that information to develop and to have these safe construction sites. We need to have the accuracy. This is extremely important when we want to have safe sites and have the information in the ground properly located. Exact locations or very close locations is a critical role in this. And of course, the case studies, which you'll hear today from us and from more, maybe perhaps in the sessions today, where this information is being combined to give you a better picture of the whole site. And this is how the information is being used. And finally, the development of it going forward, how we go forward, how we start integrating information from outside. So maybe you've collected a site and you pulled in information about the weather it was on that particular day. You know, it was rainy or cold. You know, maybe the soil is clay. Maybe, you know, the soil is sand at the location you're at, and you can use that before you even go out to the site to help you be more efficient, to be more productive. And these are the kind of things of the future. These are the kind of things that we see moving forward, and we want to be a part of it. Thank you for your time. I think that's through my slides here. We've left some time for your questions. I hope that you have a chance. I'll turn it over to Gavin to moderate the questions. And again, I hope you enjoy your day and pick something up and take it with you.
Well, hey, thank you, Clinton and Stephen. You captured what I had hoped in that session, and like I said, I've been pushing my GPR around for a few years and seen the evolution even in that time. This idea of, you know, not just 2 sensors on a GPR, and then having to read the tea leaves of the hyperbole graphs. It's like reading a sonogram. But multiple arrays on it, and like you have a big trailer mounted one with, I think it's 39 sensors or more, something like that.
40 sensors, I think, for the EM, but you have to crawl basically with that because it's an older sensor array, and I think the top speed is about 16 kilometers per hour. It's not fast.
Well, it's I tell you what, what gets provided, because you've got the multi-sensors looking from different aspects, is able to sort of do that pipe detection. But I want to get to the questions from the users, from the attendees today. This question from Omar in South America. Well, it's a common question on this. It has to do with the precision. You know, single or dual frequency GPS. He didn't mention about tying a total station in and prisms, but perhaps you guys could talk about that a little bit. How are you ensuring the horizontal precision, well as the vertical? Oh, Stephen, you're muted.
Yeah, sorry guys.
No problem.
Okay, here we have the dangerous questions, don't we? The X and Y positions. So the majority of people out there are more than happily familiar with an RTK solution. So GPS, GNSS scenario, and if we set our limits, I have all mine set at 20 mil. So my machine won't record any more than a 20 mil error. Now let's get into the real world of how accurate do we want things to be. If we're going to dig a hole in the ground, is 20 mil enough? So inside the software, we have set limits written to either discriminate and keep the accurate measurements. That's more in the DXplore stuff. For the larger systems, the arrays, we're quite happy that the software works out because we have our, as you know, if you're running a Stream C, we're at the beholder of when the GPS drops out. We can't manage that, so we can only go with what we've got. We do have the ability to post-process afterwards if we think that some areas are out. So X, Y, Z, we have to go with what we've got live. Post-processing, guys, is really where we can nail down anything that we think is going spurious. So I can do it live with GPS. I don't want to go on too much. Total station, if we can resection into a live grid, we've got a little bit more control over it because we don't lose control, we don't lose lock. We can kind of keep it happy with the prism running. It's a little more complicated than an easy, oh, it's all within 10 mil, which some manufacturers will tell you, yes, it's accurate all the time and it does 10 mil all the time. Got to be real about these things. If we're using GPS in an urban environment where there's buildings, I predominantly would say switch to total station if you're going to do that, because we've got more control over what we can do with. We haven't got signals bouncing around, we haven't got multipass, we haven't got things in the way that are going to shield the signal coming to us. It's a complicated answer, but the machines kind of take control of things for us. And if we can post-process, we can look for that ourselves too.
Okay, got to move on to one of the first questions anybody has when they're looking at GPR. How deep? Now, how deep in GPR and how deep in the hexagon system? And I thought this question when I first looked at GPR about a decade ago, and I found a study done in Siberia where, they were able to go down to 200 feet, but the problem was you'd have to wear lead underwear. The FCC limits the emissions. Perhaps you can talk about depth and talk about, soil types, clay, moisture, and how that affects the depths of the GPR and your GPR can reach.
Yeah, the question answer is it depends, and it depends on a lot of things. Soil types, conditions that you have around the area. We talk about GPR depth of some of the systems we have, some of the single array systems we have reaching down to about 2 meters, so about 6 feet. But if I take it to maybe Ohio, I might get down to 4 feet. If I take it to Arizona, I might get the full 6 feet because of the different types of soil types that we have here. And this is some of the misleading things people may misunderstand. Or if it's been pouring rain, then I will have a different performance on the radar depth. So it depends on it. We try to minimize the published answers from Hexagon, from Geosystems of about 6 feet on the depth. But again, that will limit to the actual soil conditions of it.
Okay, a question from Jeff. Does DS Explorer use standards for integrating data from different sources, GIS, CAD, EM, and GPR devices?
That will make them.
Yeah.
I can do it if you want. So DS Explorer, yeah. So we can bring in Esri formats, we can bring in DXFs, we can work with live GPS streaming to Google Maps. So input is quite simple. Export is simple again. We can export to Esri, we can export to DWG, DXF, and the new MC1 format for machine control. So in and out is okay. A future software version will see us hopefully stream data live into the DXplore software within the ML device. Currently, we're traditionally marking and statically marking that into the radar scan. So mark on floor, you can position a point of interest if you like, live in the data, and this then enables us to edit that point and elevate it with the actual locator depth. So that's where we are at the moment with it.
Okay. A question from MW. The GPR multi-sensor array, does it have different antenna polarizations, or is the sampling so dense that it doesn't really make a difference?
Actually, there's two different polarizations on it. We have, on some of those sensors, we have 40 different arrays on it, and there are clusters of arrays that are orientated 90 degrees to each other so that we can get all the information that we want out of it. So yes, there's definitely some different polarization in there. They're not so crammed in there. You kind of have to do this anyway because of the way the radar works. You need to have these orientations in here, so it's important that you do have this polarization in here so that you can capture everything in the ground. So there's definitely two areas of the array, or of this multiple array, that are going in different directions.
Okay.
I don't know, if Steve, if there's anything else to add to that. I think that's correct on this part.
Yeah, I mean, the array systems use HH and VV, so anybody familiar with GPR will know that it's how the signal is generated, either it's horizontal or it's vertical aperture. Yep. So it's kind of normal stuff, really, for the arrays. The arrays, because the antennas are so small, you know, you can get your scan spacings down to 5 and 6 centimeters apart. This is the key of the arrays. The scanning sensor, the scanning is so close together and in both directions. It collects a phenomenal amount of data really quickly with only one pass.
Okay.
So
we have to wrap up. Just a note to the attendees: the Q&A at the end of each 45-minute session is the last 10 minutes, and we tend to get a lot of questions with 1 minute left that we can't get to. We will try to ask those later in the day if we can. So also a reminder, don't put questions in the chat box. We might not see them in time. Put them in the Q&A box. We are keeping a close watch on that. Gentlemen, thank you very much.